Welcome to this lecture on the neurobiology of addiction. Today we will be discussing the brain and certain aspects of the brain that are involved in the addiction process. We hope that the material in this lecture is slightly different and new and supplemental to many of the things you've probably heard in other ADRS classes or already have read or learned about addiction. Before we talk about specific aspects of what happens in the brain and drug use, we first need to talk about administration. And I want to apologize up front. I'm going to move kind of fast through some complex material just because there's a lot to cover. However, know that there is a lot in your book, that your course textbook, that can help you understand this better if it seems difficult to follow in this lecture, but we will do our best. So first we must talk about administration. Drugs have to get to the central nervous system to have an effect. How do they get there? Well, they get there by us somehow getting them into our bloodstream, and that is called the method of administration. The three most common types of administration are inhalation, oral administration, and injection. The method of administration matters because how I administer a drug determines how quickly it gets into my bloodstream and how pure it is when it gets in my drug's bloodstream, which will impact how intense its effect is. For example, if I take a drug orally, it will go through a filtration process as it goes through my digestive system, and as it's broken down and metabolized and finally enters the bloodstream. So it will take longer to get into the bloodstream and to get to the brain, and by then it may have a reduced effect because of the filtering process that it's been through. However, if I inject a drug directly into my veins, it enters the bloodstream immediately, and it's in a pure form. The compound has not been metabolized, and it quickly reaches the brain and may have a much more intense effect. So that's administration is the initial process, but then drugs have to get through the blood-brain barrier. How they get through the blood-brain barrier depends on the type of compound they are. The blood-brain barrier does not let everything through. It only lets certain things through. Certain types of drugs get through because of and depending on the type of compound they are. Another thing that determines or influences what passes the blood-brain barrier are situational factors like stress. For example, if someone is very stressed and they have a lot of cortisol in their brain, because that is a stress hormone, the blood-brain barrier is thinned when there's stress and cortisol present, and it's easier for different compounds to pass through it. And this will impact how drugs enter the brain. Once they get to the brain, they've entered the central nervous system, or the CNS, where they can have their main effects. Drugs in the central nervous system have their effect either directly or indirectly by binding with or influencing processes associated with receptors on neuron cells. On the top right of the screen, you'll see a key and a lock. A neurotransmitter is like a key, and a receptor is like a lock. In the brain, neurotransmitters connect with receptors, and they bind, and they pass information, and we'll explain this process a little bit more. However, what you need to know is that only certain keys fit certain locks, or only certain receptors fit certain neurotransmitters fit certain receptors, and that is how the brain operates and passes information and functions. And we'll talk about that a little bit more. But what you need to know about that process right now is that drugs can trigger activation of neurotransmitters. So they can come in the brain and they can get the brain to release certain neurotransmitters that go and bind with receptors and pass information, or they can act like a neurotransmitter themselves. They can trick the brain and make the brain think they're a neurotransmitter and then also have an effect. And that effect is usually that the drugs will change cell voltage, they'll create chemical cascades, or they'll alter gene transcription. So let's talk about this process a little bit more. If you look at this, the green part here on the left is the end of a neuron cell called an axon, with axon terminals. The orange dots here are neurotransmitters that are inside of a vesicle that they are being carried in. An action potential is when an electrical charge that's associated with calcium and potassium and some other things, we won't get into that too much here as it's very complex, but as it passes down the cell, it signals to the vesicle to release the neurotransmitter at the axon terminal and out into this space, which is called the synaptic cleft. Now, next to this neuron cell is a neighboring neuron cell, and these blue pieces here are called the receptors that exist on the dendrites of a neighboring neuron cell. A neurotransmitter in this space then floats around until it connects with and binds to a receptor on a neighboring cell. When it binds, it passes the information along that it's responsible for. For example, dopamine is a pleasure chemical, pleasure neurotransmitter. Transmitter. It's responsible for learning and motivation and reward. Whereas serotonin, another neurotransmitter, is responsible for sleep and mood and even some aspects of memory, although that's more driven by glutamate. However, so that's a binding process, and that is how information is transferred, and when that information gets passed on, it also triggers an action potential or an electrical charge in the neighboring cell, and the process repeats itself, and thus information is passed throughout a network of neuron cells throughout the brain. And this creates pathways in the brain. Antagonistic drugs, then, are drugs that decrease the amount or transmission of a specific neurotransmitter. So a drug may cross the blood-brain barrier, and it may come in here and bind with a receptor or the receptors on neuron cells. Then when the natural process occurs, and let's say dopamine is trying to be passed from one cell to another, it cannot bind with the neighboring cell because the drug is blocking it. This is an example of an antagonistic drug, and makes it unavailable to transmit information through neurotransmitters. On the other hand, agonistic drugs are drugs that increase the amount of transmission of a specific neurotransmitter. The way they do this is, one, through binding to receptors and activating them as if they were the neurotransmitter themselves. So instead of binding and acting as a blocking mechanism, they bind and their key fits the way the natural neurotransmitter fits, and this neighboring cell thinks that it is dopamine, and thus it triggers that effect of increased amount of transmission of dopamine. However, another way that could happen, way number two, is that it binds, it doesn't act like the transmitter itself, but it causes the cell nonetheless to release a charge and information that ends up resulting in the transmission of a specific neurotransmitter. This is very complex. If you don't understand it all at this point, that's fine. Just know that there's neurotransmitters, there's neuron cells, and they pass information. And when they do, when neurotransmitters bind with receptor cells, it's called a cell firing. There's a law in neuroscience called Hebb's law, and that is that when neurons fire together, they wire together. When neurons wire together, it creates pathways in the brain through which information gets easily passed, or patterns of learned behavior and learned information gets carved into the brain and becomes instinctual or natural, or second nature, if you will. And so this is how addictive pathways can get carved into the brain. Drugs come in and they either get a cell to release dopamine or excess dopamine, or they act like dopamine itself, and they create a pathway in the reward circuitry of the brain that gets carved in deep, that leads to compulsive behavior. That dopamine pathway goes from the mesolimbic area up to the prefrontal cortex, and so thus it affects conscious decision making and choice, although it began as an unconscious process. This is part of what is called the dopamine hypothesis. Dopamine is a feel-good neurotransmitter, again, associated with reward and the feeling of pleasure. It is inherently connected to survival, and it promotes survival behavior. It is what signals to us that we need to do something to stay alive, like drink water. And when we do, we experience pleasure, especially when we're extra thirsty, so that we'll learn it and do it again. In the process of addiction, changes occur in the brain such that the brain learns that the drug or addictive behavior can become the purpose of existence or survival itself. Everything else is just supplemental. This is going to impact motivation, memory, and goal and behavior-oriented processing because the dopaminergic pathway also involves the prefrontal cortex and the orbital frontal cortex, which are both involved in motivation. Okay, to end this lecture, we're going to talk a little bit more specifically about the conscious part of the brain, the prefrontal cortex, where we make decisions and make choices and direct our behavior consciously. As learning animals, it's important to understand that we are supposed to either assimilate or eliminate, and those are just fancy words for, as we experience things in our life, either we want to embrace them and make them a part of our life or get them out of our lives because they're destructive or dangerous for our lives. Our prefrontal cortex is a massive, maybe massive may not be the right word, but a very complex calculator to help us make those decisions. There are 4 different areas of the prefrontal cortex. The right and left dorsolateral areas of the prefrontal cortex are called the cognitive control system. The right dorsomedial and left dorsomedial, here in blue and green, are called the social brain network. The yellow and red here, the dorsolateral areas, the cognitive control system, are responsible for working memory, attention, inhibition, calculating risk, deciding whether to do something or not do something, whether to approach or whether to avoid. And they pass information across and they talk to each other, and they need to do this because the right side, the red side here, is responsible for processing negative things that could be dangerous, things we should avoid, inhibition processes, whereas the left side, the yellow, is responsible for processing more positive, euphoric types of things we should approach and embrace and assimilate in our lives. They talk to each other, and then they help us make decisions about risky behavior and what we should or should not do. Okay. The medial areas, the social brain network, they're responsible for our highest order of executive thinking. They help us as human beings learn to think about how other people feel and what they might be going through, which helps us be altruistic. It's responsible for altruism and really caring about another person, which helps us in our relationships. It helps us manage the emotions and the decisions in our relationships. And again, the right side is responsible for avoiding negative type processing, potentially destructive things, and the left side is more the euphoric approach, embrace type of processing. This calculator, and they also speak across the corpus callosum, the right and the left dorsomedial areas, and together they all speak and they kind of help calculate risk and reward and should we do it, should we not. They evaluate the situation and then we make conscious choices. So let me show you a little bit how this works. If I were to ask you to participate in an experiment, or if you wanted to, you could raise your hand and volunteer if you would like, but I said, why don't you come up here and you pretend I have this gumball machine, and if you get a yellow, I'll give you a quarter, but if you get a yellow, I will give you $1,000. That's it. No other stipulations, no other rules. Most of you would raise your hand and say, sure thing. Why not? No risk. The left side, the left hemisphere, would communicate with the right hemisphere, and it would be determined that there's very little risk here and great chance for reward, so let's approach, let's do. Now, if I changed the rules of the game and I said, if you get a yellow gumball, I give you $1,000, but if you get any other color, you give me $1,000, many of you would put your hands down and decline to participate. This is because your left side and your right side talked, and this time the right side had said to the left time, really be careful here. We may want to avoid this. This could be destructive. You don't have $1,000 to lose right now. And you might put your hand down. The way that pathways get carved in the brain through the dopaminergic or through the reward circuitry of the brain, due to the effects of drugs on neurotransmitters, it carves in pathways that alter and distort the reality of an addict. For example, This is how an addict might see the world when I present this option to them. They will look, and the world to them, the middle here is still reality. The rest of the population sees all the colors of the gumballs, and that is true reality. But the distorted reality is for the addict is that everything looks yellow, and how could I lose? So they approach because they don't see risk or experience the consequences. Now, this may not be universal for every addict. Some addicts may still know what's going to happen and still do it anyway, but it's nonetheless an impulsive behavior. Then when they lose and they get a blue, they wonder how that could be, and they want to go double or nothing because, they must have gotten the only blue gumball at the very base of the stack there, and so let's try it again. Now, those are impulsive processes that lead to people jumping in and doing things that could be destructive despite the consequences, and just to have a rewarding experience. There are also compulsive disorders associated with decisions in the prefrontal cortex, and an example of that would be this. Let's say I told you that if you came up and turned this gumball machine, if you got a red gumball or a pink gumball, it's hard to, let's go pink. If you got a pink gumball, you would give me $1,000. But if you got any other color of gumball, I would give you $1,000. Many of you, your brain would communicate, and you would see that there are many more other colors, thus meaning higher odds of me giving you $1,000 than you getting a pink gumball and having to give me $1,000. And you might then raise your hand and opt to participate. Compulsive people, however, who have excess activity on the right side of their brain can have a distorted reality such that they see the world this way. When they look, all they see is pink. And they think, I will lose no matter what. Why would I do this? I am not going to approach. I am not going to participate. They consistently avoid, and their goal is just to not make bad things happen in life. And this concept introduces the idea of impulsivity and compulsivity. Both are instinctual processes that are driven by unconscious processes, but they involve the conscious processing of the prefrontal cortex that's been altered through pathways. People who are impulsive, often all they want to do is make something good happen in life, and who cares if something bad happens. Whereas people who are compulsive often don't care if anything good happens. They just want to make sure that something bad doesn't happen. Maybe a metaphor I could use that would help you understand this is that of the bumper cars at the theme park. Many of you have probably driven in these, and you all know the kids I'm talking about in these cars. As I watch them, some kids, their only goal is to wreak havoc and bump into everyone they can for the 5 minutes they get to drive the car. Whereas other kids, their goal is to spend the 5 minutes trying to avoid getting hit. Those trying to wreak havoc would be our impulsive kids in this example. Those trying to avoid being hit would be our compulsive kids. Ideally, we see reality for what it is. Our brain communicates, and we make decisions based on all the information available. This leads me to the very end of the lecture, talking about the neuropsychology of addiction. There is a theory called the impaired response inhibition and salience theory. What this theory means is that most people, or people without addictions, have normal stimuli come into their lives throughout their day, and their brain activates and processes that information. For people with addictions, however, their brain activates on the outer regions, the dorsolateral areas, typically only in response to stimuli that are associated with their addiction. What this means is something like this. Let's say I live in Utah. That's where I grew up. I remember John Stockton hitting a three-point shot that put the Jazz into the finals for the first time past the Houston Rockets. When I see this, my brain may light up. Show this to someone in the middle of an addiction, their brain will be silent, like you see on the right. Let's say you take them after to a beautiful hike where you enjoy a sunset behind a mountain. Again, their brain, no activity. Crickets, silent. But if I show that alcoholic a cue of alcohol, then the brain has hyperactivation on the exterior areas, the dorsolateral areas, that processes that information. Thus, they are biased and attuned to addiction-like cues. To further understand this, I'll tell you about a couple of studies we've done in the Center for Addiction Recovery Research. This is an image showing activation in response to alcohol-related cues for alcoholics in recovery. You'll see here that there's a lot of activation on the left side, which would be the approach, do this, and some slight activation here on the right side, and both of these are considered the dorsolateral areas of the prefrontal cortex. The literature and scientists believe that this type of activity is associated with craving, preoccupation, so thoughts, I can't think of anything else but drinking alcohol, and anticipation of getting to drink alcohol. Particularly that activation there on the left side. What this picture is signifying right here is this is activation that people in early recovery from alcoholism have, that people in later from later recovery from alcoholism don't have. So what this means is that over time, as one stays abstinent from alcohol or from their drug, this hyperactivation that comes when they're presented with cues in their life of alcohol, this activation that makes them crave, that makes them think about alcohol, that makes them anticipate getting to drink, that activation fades over time as they stay sober. One last study I wanted to show you is a study we did about coping skills and the prefrontal cortex. We know that things that fire together wire together. The contrary to that law is that things that don't get used or that don't fire together die and get swept off. This explains atrophy in the brain of people with addiction. When certain parts of the brain, such as the medial areas, in particular in this case, don't get used, they die and they weaken, kind of like muscles that don't get used atrophy. Well, it's known that alcoholism leads to lots of atrophy in the prefrontal cortex, and one of those areas is the medial area where we do our social brain network and relationship processing. We ran a study and we learned the following from that study, that alcoholics in recovery, or someone in recovery from alcoholism, when they have coping skills, when they learn to behaviorally cope with life and turn and deal with their problems instead of try to escape their problems, you'll see a yellow circle here on the right dorsomedial prefrontal cortex. I won't explain at this point why there's two different pictures here. But this activation is activation that's associated with persons in recovery who have high coping skills to deal with stress. This is activation that those people have that people in recovery who have low coping skills to deal with stress do not have. Meaning people who are just abstinent, they may get decreased craving and preoccupation and anticipation of use, but abstinence alone is not recovery. There are still parts of the brain that until you learn how to cope with life, cope with stress, deal with things differently, remain inactive. But as you learn to cope, as you learn to do things differently, your brain fires and rewires and changes, and these parts of the brain that were previously dead, for lack of a better word, come back online. And this regional activity, particularly as we've shown it here, again is associated with high executive thinking, goal planning, thinking of relationships, and I would have you note that it's on the right side of the brain. Remember, the right side is about, maybe I shouldn't do this, maybe this could be destructive. So if this is in response to alcohol cues for a recovering alcoholic, it could signify that because they learned to cope, they've brought back a part of their brain that can say, hey, wait, what about my future goals? What about my relationships? What about everything I've been trying to create in my life? And the brain can start to heal that way. That concludes our lecture on the neurobiology of recovery. Again, hopefully it gave you some additional information into the processes of brain structure, pathways, and choice, and how when we say the prefrontal cortex gets hijacked, you can understand a little bit more how that happens. This is very complex material. Some of it you can gain by reading closely in your chapter, but I hope you've enjoyed this presentation and wish you the best on the following lectures. Thank you.